Eric.
Hi.
How are you doing?
Well, how do I run into you here in Cambridge?
I follow you around. You didn't know that?
Yeah, oh, you're my groupie now. Yeah.
Well, I wouldn't go that far, but yeah.
Okay.
We got a lot of them on 9. And we're here with Simon Peyton Jones again.
Hi there, Charles.
How you doing?
Good to see you again.
Nice to see you. So, what's going on?
So one of the things I've been thinking about recently is we got this this big picture going on. I'm going to draw a picture. So it's like this. We got so here we got programming languages, and we got ones that are useful, and here's ones that are useless.
Okay.
And here's ones that are unsafe, and here's ones that are safe.
Okay.
By which I mean safe, I mean very limited effects. Effects, I mean side effects.
Side effects.
Limited, controlled effects. And this is any effects anywhere. And this up here is C, right?
Okay.
And down here is Haskell. But actually also here is C# and Java and C++. Pretty much every mainstream language is in this useful but unsafe camp.
Now let's talk about that for a second. Even C#?
Oh, sure.
Uh-huh.
C#, what does a C# program do? It's an imperative program. It's a sequence of steps. Every line says, do this, then do this, do this. When you call a method, often it has no arguments and no result. It may have some arguments, but no result. And why? Because its sole reason for calling it is to have an effect on the world, to change the state of something.
Interesting.
So it's fundamentally effectful.
Okay.
And this is a very powerful computing paradigm. It's what our machines do, after all. It's incredibly useful in practice.
Absolutely.
So what we'd like to go is here. This is Nirvana, right? Where we're both safe and useful.
Okay.
Right. And the real world has been gradually moving in this kind of direction in all sorts of ways over time. In fact, becoming more and more controlled. I think transactional memory is a good example of this, where we want to say, well, inside a transaction, it would really be so much better if we could control, we could make sure that we don't do, say, arbitrary input-output. That's arbitrary effects. Mm-hmm. Because inside a transaction, you've got to make sure you don't launch the missiles until you've seen a consistent view of memory. So that's an example of what I mean by a limited effect. Uh-huh. Or you might like a procedure, and you might like to say, I know this procedure is a pure function. In fact, some languages maybe even are getting pure annotations. Compilers can do a lot with those kind of things.
So this is like where link is also moving, right?
Right. Good.
Exactly, because in expressions, in the query comprehensions, you want to be there. You want to have no side effects, because then the compiler can do much more optimizations, or send it to SQL, where you don't know what happens there.
So indeed, SQL is a language like that. So there's little sub-languages that have become quite mainstream and very useful that have controlled effects. But at the moment, they're all embedded in large languages that have unrestricted effects. But nevertheless, there's a big trend. The more we think about parallelism too, the more we need to control effects. Because if you have unrestricted effects, you do things in parallel, then you don't know what the result of the program is going to be.
Absolutely.
So from the other end of the world, us sort of geeky Haskell guys have started with completely useless language, right? Because it had no effect. In the end, a program with no effect, there's no point in running it, is there? You have this black box, and you press go, and it says, it gets hot, but there's no output, right? Why did you run the program? The reason to run a program is to have an effect.
Sure.
Right? So, but nevertheless, we put up with that embarrassment for many years until we figured out how to combine in a single language, a single programming metaphor, we can combine effectful computations and effect-free ones without making them pollute each other.
Interesting.
Right? The type system keeps them apart. So we've been working from that direction. Everyone else is working from this direction, but there's a lot of cross-fertilization going on here. Mm-hmm. Right? We got the idea of STM, the transactional memory stuff, from the imperative world. Mm-hmm. We thought about it over here and added retry and or else, and are busy putting that back into the imperative world.
Nice.
There's quite a bit of cross-fertilization going on.
Or the other one with the comprehensions, right? That came from here, or that came from there to here and back.
Right.
So now, Haskell's comprehensions are kind of, getting ideas from the C# and VB comprehensions and putting them in.
Well, let's talk about that briefly. Comprehensions, definition.
Oh, comprehension, the query expressions.
Okay.
And the comprehensions is the geeky word that comes from from Haskell. So Simon just wrote a paper with Phil Wattler where they kind of extend the Haskell comprehensions with order by and group by, which is something that we introduced in C# and VB.
Outstanding.
Where we took the original idea from comprehensions from Haskell. So it's a kind of nice, way of Yep.
So here's a Haskell comprehension, which you read the list of all x such that x is drawn from x's and x is bigger than 0. And in LINQ or SQL, you might say from x's select x where, or something like this, and where, and here's a filter expression. But then these guys, you know, so over here in the LINQ world, and indeed in the SQL world, there's also order by and group by, and so we're busy that's right, a whole bunch of other stuff here, and we're busy figuring out maybe we can steal some ideas from over here and put them back into Haskell.
Absolutely.
So it's a very, very productive sort of synergy going on here.
Mention that this stuff started out in mathematics.
Who's this guy? Who are you, sir?
I'm Butler Lamson.
All right, another fellow researcher.
That is right.
Oh, but he is a great God before whom we bow. So.
Yes, exactly.
All right.
Let's still know
Let's see the bows in action here.
So I'm short-circuiting a lot by saying Haskell here, right? But Haskell's predated by lots of other languages, which is predated by mathematics. Yeah. And now we have to go and judge a competition.
Mathematicians wouldn't recognize this ordered by and grouped by.
They will, once we put it back into Haskell, they will.
Mathematicians will, or just
Sure.
Haskellites?
Outstanding.
Okay.
How are we doing here?
Hey, Fabian.
Charles, you've stolen my judges.
So the judges now need a judge. What a great panel of judges.
Oh yes.
Outstanding.
It's a very outstanding panel.
Always
brief.
great to talk to you guys.
Quick brief for them and then we can
Sure.
start again. So,